Welcome. This is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York. And this is Exploration. Every week on Exploration, we discuss the fascinating world of science, as well as its impact on society. And today, once again, we're going to try to answer some of the volumes of emails that I get. And again, I have to apologize for those people whose emails I can't answer. But one way to answer as many as I can is to simply answer them on radio. And so that's what I'm going to do for the first part of Exploration. Well, even though, of course, we are in the middle of the presidential election season, and the election is reaching a feverish pitch between Hillary Clinton and Donald Trump, it's also good to always look at the lighter side of things. So, which do I prefer, Star Wars or Star Trek? First of all, I'm a fan of both. I think I've seen every single one of the episodes of Star Wars and Star Trek. But personally, I think I prefer Star Trek because it probes societal questions. It's more than just ray gun battles and battles with monsters in outer space. You know, when I was a kid, I used to love to watch the old Flash Gordon series that they would rerun on television with Buster Crabbe. Well, another person who liked that very same Flash Gordon series was George Lucas. And George Lucas said, quote, "After Vietnam, I wanted Flash Gordon." And Flash Gordon became Star Wars. In fact, almost scene for scene, you can see the enormous impact of Flash Gordon on the Star Wars series. But hey, it's great for ray gun battles, for shooting monsters from outer space, for shooting the bad guys. But it's not so great when you start to look at societal questions. And that's what Star Trek does. Star Trek gives you a vision of a potential future, a future in which all the nations of the earth are unified, that races work together towards a common goal, and societal questions, the question of overpopulation, question of rich and poor, the question of pollution, things like that are actually addressed in the Star Trek series. Now, just last month, I had the privilege of being interviewed by William Shatner. William Shatner is doing a new program for Netflix about Star Trek. And, of course, he wanted to put some scientists in the program. So I had a chance to actually be interviewed by William Shatner via Skype. And in that interview, of course, William Shatner admitted that he was not a scientist. He did not know anything about black holes and warp drive and time travel and stuff like that. But he was fascinated about the vision, a vision of a future society and a future world. For example, one of my favorite episodes of Star Trek concerns a space capsule that was created in the 20th century containing people who are dying of cancer and fatal diseases. They were shot into outer space in the hopes that at some point in the future, perhaps hundreds of years in the future, they would be revived and live again. Well, Star Trek takes place in the 23rd century. They find this capsule floating in outer space. They retrieve it, and sure enough, they're the bodies of people suffering fatal illnesses in the 20th century. Using 23rd century magic, they're able to revive all these people. And one of them was a banker. And the first thing that he asked is, "What century am I in?" And when he realizes he's in the 23rd century, he says, "Oh my God, I did it. I did it correctly." He predicted that at some point his investments would be worth a fantastic amount in the future because it's been compounding annually ever since the 20th century. And the first thing he asks for is, "I want to talk to my banker. I want to know how much money I have." And then the crew of the Enterprise stares at him, and they basically says, "Money? What is money? We don't have money in the 23rd century. When you want something, you simply ask for it on a replicator." And then all of a sudden, all the dreams of this banker go crashing down because he realizes all his investments are basically worthless because in the future, there's no such thing as money. Now, if you think about it, that's pretty seditious. And these are the kinds of questions that they ask in the Star Trek series. Now, one favorite episode is the city on the edge of forever with the old Star Trek crew. In that Star Trek crew, they meet a wormhole in outer space, and who lives on the other side of the wormhole? It's Joan Collins. That's right. It turns out that the crew of the Enterprise go back in time to Earth back in the 1930s as America gets ready for a potential world conflict with Nazi Germany. And Joan Collins, unfortunately, gets in the way. And she was destined to become a lover or an acquaintance of FDR. And the very fact that she lived meant that she would convince FDR not to go into World War II, which would change the course of history. And so they suddenly realized that a romance that is building up between Joan Collins and William Shatner could derail the whole thrust of the future. So in other words, William Shatner has to make a decision. Is he going to go ahead and basically allow his girlfriend to be killed in an accident, or will he allow her to live in the future, derail the progress of world history? Well, of course, it is science fiction, but it does raise a question. What happens in the future if you can't tinker with the past, and you have to make a decision whether or not your personal interests are worth more than the destiny of world history? That's the question that confronted William Shatner in that episode of Star Trek. So, just to summarize, I like both Star Wars and Star Trek. However, in Star Trek, you get to delve into very meaty social questions that involve human conflict and human choices. And that's why I think that Star Trek is perhaps the better of the two. Also, here's another question. How come birds can fly and airplanes can fly, but we can't? Well, that's a very interesting question. And it's a question asked for thousands of years as the ancients wondered, how is it that birds can fly? Is it the feathers? Is it the flapping? I mean, what is it that birds have that we don't have? And the answer was, well, actually none of the above. The answer is, it's not the feathers so much as the shape of the wing. The wing is in the shape of a airfoil. If you have a cross-section of the wing, it looks like a teardrop. And that means that air rushing over the wind has to go a farther distance and has to speed up versus the air that goes underneath the wing. And according to Bernoulli's principle, which is based on the conservation of energy, the faster the air goes over the wing, the lower the pressure there is. So in other words, to put it crudely, there is a partial vacuum that occurs above the wing versus the air pressure beneath the wing, which is normal. And that causes lift. So in other words, the ancients got it all wrong. It's not so much the flapping, it's not so much the feathers, it's the shape of the wing, and that allows birds to fly. Plus the fact that birds have, well, hollow bones. They're very light compared to humans. Now, of course, artists like to draw pictures of angels that look just like us except have wings. However, if you were to actually build a wing like the wings you see in these paintings during the medieval period, you realize that these angels cannot fly at all, for several reasons. First, their bones are not hollow at all. They would have to have hollow bones. They would have to be much lighter. Second, they would have to have enormous muscles in the back of their body. And third, the wingspan must be much larger than those depicted in these paintings. So in other words, if you ever seen people with gliders with wingspans that are huge, and they, of course, can jump off mountains and begin the process of gliding, you realize that the gliders are very light, the wingspans are very, very long, and, of course, the wings are in the shape of an airfoil. So, in other words, angels don't cut it. Angels essentially violate the laws of physics because, A, their bones are too heavy, the wingspan is too short, and their muscles are simply too weak in order to flap their wings and navigate in the sky. Another question that I get is, well, how come planets and stars are round? How come the sun is round? I mean, how come the sun can't be square? How come the earth can't be like a cube? Why is everything round? Well, first of all, not everything is round. Small objects like asteroids and meteors can be shaped like a potato. And that's the clue as to why everything is round. It gets to Newton's laws of gravity. Newton's law of gravity says, more or less, gravity sucks, but gravity sucks evenly. Therefore, if I have a potato and gravity is then compressing the innards of the potato becomes spherical. So in other words, in outer space, if we have a ball of hot gas, originally it may be irregularly shaped, but because gravity sucks evenly, eventually it becomes round. Now, at one point in the Earth's history, in fact, several points in the Earth's history, the Earth was not round. We know that roughly 4.1 billion years ago, an object the size of Mars plowed into the Earth and blew out the moon. So what did the Earth look like back then? The Earth probably looked like Pac-Man, with a huge, gigantic, pie-shaped chunk that was blown out of its guts, which eventually condensed into the moon. But both segments eventually became round. Why? Because gravity sucks evenly at the same distance from the center, and therefore, even though the moon originally was probably shaped like a potato, it also became round shape, and the same thing with the Earth. So gravity basically compressed the Earth so that the Pac-Man shaped irregular Earth became round. That's why the sun is round, and so the larger the object is, the rounder it is, and that's why asteroids, which can be very small, we have pictures of them now, show that they are essentially shaped like a potato. Here's another question. Everybody likes to use the GPS system because it tells you where you are. You can locate your children. People can also locate where their spouse is if they think their spouse is cheating on them. If you are a camper, you can locate where you are in the middle of the woods. But how does GPS work? Who pays for it, and how did it come to be? Well, believe it or not, it came to be because originally it was a weapons program. People wonder, for example, how did the Internet come to be? All of a sudden it just was there. Well, it was also a military weapon. The Internet was not invented by Al Gore. It was invented by DARPA, a branch of the Defense Department. Originally, it was called DARPANet. And then eventually, in 1989, DARPANet was declassified. All its codes were given away for free by the National Science Foundation because the end of the Cold War was in sight. And after 1989, the Internet, as we know it, was born. It's amazing. A military weapon pretty much given away for free, changing world history in the process, and that's called the Internet. Well, the GPS was also a byproduct of the Pentagon's work. The Pentagon, for example, during World War II, realized that there was an enormous amount of waste as well as wasted lives because of saturation bombing. The bombing of Dresden, the bombing of Tokyo. Hundreds of thousands of people were incinerated, mostly unnecessarily, because about 90% of the bombs missed their target. It was a waste of money, and of course, it was a waste of the lives of hundreds of thousands of people. And so the military wanted a way to, well, navigate accurately. Plus, if you're going to have nuclear war with the Soviet Union, you want to know where your nuclear warheads land. And because nuclear warheads are hardened during the height of the Cold War, it means you have to place a hydrogen bomb pretty much on top of a missile silo that is 6,000 miles away. And so how are you going to do that without a very precise navigation system? And that's where the GPS comes in. A handful of visionaries petitioned the Pentagon to create a system of satellites. Satellites numbering about 30 or so that circulate around the Earth at any given point, so that at any given time on the Earth, you can sight 4 satellites going around the planet. And so the GPS system is not a transmitter, it is a receiver. It is a passive device. It is not broadcasting anything at all. You're not interacting with the GPS system at all. You have a GPS system that is passive inside your cell phone, logs on to signals from at least 4 satellites, and then the GPS system triangulates where you are. Now, how does it do that? Because when a satellite moves toward you, radio waves are compressed. When the satellite moves away from you, radio waves are stretched. This is called the Doppler effect, and it works for sound waves that also. For example, ever since you were a child, you've heard the following sound. Now, Now, what is that? You've heard that all your life. It's the sound of a car approaching you, passing you, and moving away from you. So when sound waves are going toward you, sound waves are compressed like an accordion. When sound waves move away from you, they're stretched like an accordion. And that's why the frequency changes. Well, in the same way, you can calculate the velocity of a satellite in outer space using the very same physics. So by logging onto 4 satellites, you can triangulate yourself, and that's how your cell phone allows you to locate your distance within a few feet. And they tell me that on a good day, you can locate your position to as low as 6 inches. And this could be very important because one day cars could become driverless. You simply hit the switch and the car locates its position using GPS and off you go. Now recently, of course, last month, there was a very prominent fatal accident with a Tesla motor car where a truck made a left turn in front of an oncoming car. The car that was oncoming was a driverless car, and for some reason the computer was confused. It did not stop. It smashed into the truck, killing the driver of the driverless car. This was very bad publicity for the driverless car program. But the question is, what was at fault? Was it the GPS? Was it the computer? Why did we have that fatal accident? Well, first of all, it was not the GPS system. The GPS system, as I said, is a passive object. It simply sends waves, you receive the waves, and then triangulate your position on your cell phone. So it wasn't that. So why did we have that fatal accident? Well, of course, studies are still being made to find out what happened, but I would venture a guess, and that is it's not the GPS, but it's the radar system and the system that analyzes the radar. You see, in the fender of a driverless car is a radar system that detects obstructions, other cars. GPS doesn't do that. GPS only locks onto where you are located. It does not lock onto the presence of children, dogs, and what have you. That is the purpose of a radar system in the fender and a computer that analyzes this data. So probably the artificial intelligence system, the software, as well as the radar system malfunctioned. Now, of course, you're going to have to analyze that very carefully. But again, it's probably not the GPS system that broke down. Well, another question I sometimes get is hurricanes and your bathtub. When you pull the plug on your bathtub, does the water go down clockwise or counterclockwise? And for that matter, hurricanes. Hurricanes in the northern hemisphere, if you've watched the news during storm, well, those hurricanes go counterclockwise. And then the question is, well, below the equator, do they go clockwise? Do they reverse direction? Well, the answer is something that you can figure out tonight. Take a bath, fill up your bathtub with water, pull the drain, and simply look to see which way the water drains. Normally, it should drain counterclockwise, but, and this is a big but, you can use your finger to spin the water in the other direction, and it will reverse direction. This is called the coriolis force, and it has to do with the fact, believe it or not, that the Earth spins. The spinning of the Earth is responsible for making hurricanes go counterclockwise. You see, as warm air rises, the Earth spins slightly beneath the warm air as it rises, and that gives rise to a net spin. Okay, you got that? Hot air rises, especially in the Caribbean, and as hot air rises, cold air comes in from the side. And because the Earth rotates slightly in the meantime, it means that that puts an extra twist in the air, and that's why in the northern hemisphere, hurricanes go counterclockwise. While below the equator, they go clockwise instead. However, it's a very faint effect, and you can reverse it in your bathtub or your kitchen sink. So try it today. Simply pull the plug, and if everything is calm, if everything is perfectly motionless, it should drain counterclockwise. But it's very easy to reverse that direction. Well, here's another question I get, and that is, how do birds navigate? You've probably seen these science specials where birds can navigate thousands of miles. In fact, just recently on the internet last week, it was mentioned that one group of birds was actually clocked going around the entire planet without a stop. This is amazing that birds can actually navigate around the entire planet Earth without stopping, and we prove that by tracking them with radio. Well, how do they do it? I mean, think about it. If you're way up there in the sky, you can barely see what's on the ground, and if you're flying thousands of miles, how can they possibly navigate? Well, the short answer is we don't know. Yes, we scientists don't know everything. There are many theories, and perhaps one of these theories will pan out. One theory that perhaps has some weight is the fact that animals use magnetism to navigate. Perhaps fish do that, perhaps whales. Of course, the navigation ability of animals is nothing short of astounding. They're able to navigate and spawn even though they have to go hundreds, thousands of miles to do so. Now, it turns out that magnetite is found naturally in cells, and it will lock on to the direction of the North Pole. And it's possible that these animals have sensors which can then detect which way the magnetite is aligning. However, this is still a theory, and even with that information, how do birds navigate, even knowing the direction of magnetic north? That is also a question that scientists are still investigating. Plus the fact that perhaps in the next few hundred to next few thousand years, the poles will actually reverse. That's right. We're going to have a reversal of the magnetic poles of the Earth. We can see that happening already. If you take a look at the strength of magnetism hundreds of years ago compared to the strength of magnetism today, you realize that even in that short period of time, gravity, the strength of gravity is weakening. And in the next few hundred, the next few thousand years, perhaps the strength of gravity will go down to zero. And then it will probably shift or reverse. This is not science fiction because it's actually happened in the past. So you don't have to worry that we're going to reach Armageddon or something when we have a pole shift. This is not a geologic pole shift. We're not talking about the spin of the Earth shifting. We're talking about the magnetic north moving. Now, we know that it moves because, for example, if you go to Hawaii and simply dig into the lava flows, when lava freezes, the direction of the North Pole is frozen in the lava. And so by simply digging into the lava in Hawaii, you can actually see that the direction of the North Pole shifted with time. So we do know that it happens. So if it happens in the future, it means that birds which navigate and fish which navigate using magnetism could be thrown into confusion. And perhaps this has happened before. Perhaps it means a certain species will go extinct as a consequence because they can no longer spawn correctly. Here's another question that I get, and that is, how do we know how far the stars are? I mean, after all, the stars are really, really far away. No one has a tape measure. So how do we know the distance to the planets? How do we know the distance to the sun, for example? How do we know how old the universe is and how big the universe is? We don't have any measuring stick by which we can do this, so how do we scientists figure this out? Well, how do you know how far an object is? You know how far an object is because you have stereo vision. Your two eyes are separated, and the left eye sees something a little bit different than the right eye. If you don't believe me, simply cap one of your eyes, and you suddenly realize that it's much more difficult to judge distances. You judge distances by shadows, of course, but in a room without shadows, you can bump into things because you don't have two eyes. This gives you stereo vision. Another way to do that is to move your head. If you look at an object across the room and move your head, you realize that objects close to you move more than objects far away. Now, the mountains. You know the mountains are very far away because no matter how much you move your head, the mountains don't move at all. Everything else moves that is close to you, but the mountains don't move when you move your head. And so astronomers, when they want to know how far the nearby stars are, what do? They move the telescope. Now, how far can you move a telescope? That sounds like a stupid question. Of course, you can move the telescope, and perhaps you can move the telescope to perhaps the circumference of the Earth. But no, you can move the telescope much farther. You could simply wait 6 months, because in 6 months, the Earth goes halfway around its orbit, around the Sun. Now, we are over 90 million miles from the Sun, and so if you simply do nothing and put your telescope in the ground and wait 6 months, the night sky will change by approximately 100 million miles. That is the farthest you can move a telescope, twice the radius of the planet Earth. And then you photograph the night sky in summer, and you photograph the night sky in winter, and compare the two pictures. And bingo! You see that the nearby stars move more than the faraway stars. So this is how we know the distance, for example, to Alpha Centauri, the closest star to the Earth, a little over 4 light years from the planet Earth. Now, more distant stars, we have to use a whole different set of measuring sticks. But yes, we can do that as well using astronomy. Now, it's also possible to calculate the distance to the faraway stars much farther out in outer space. However, that's a whole other question, and that involves using something called variable stars and even supernovae. And for that, you should consult an astronomy book. But yes, it's possible to even measure the distances out to the farthest stars in the visible universe. And in fact, in that book, Parallel Worlds, I even go before the Big Bang. What happened before Genesis, chapter 1, verse 1? What happened before the beginning? Or you can always get a copy of my earlier book called Parallel Worlds, where I discuss the possibility of, yes, calculating the distance to the farthest stars and even going all the way back to the origin of the universe itself. Welcome. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York. In the second half of Exploration, we're going to bring on our special guest today, and he's going to talk to us about the long thaw. That's the title of his latest book by Professor David Archer, and we're going to talk about what happens, well, when the polar ice caps begin to thaw out. What happens to the Earth when all the glaciers begin to melt, when the stability of the ecology of the planet Earth is at stake. So once again, our special guest today is David Archer. The book is called The Long Thaw. And now I'd like to introduce our special guest for today. He's Professor David Archer, Professor of Geophysical Sciences at the University of Chicago, and he's the author of a rather disturbing new book. And it's called The Long Thaw, How Humans Are Changing the Next 100,000 Years of Earth's Climate. He argues in The Long Thaw that not only are humans ruining the atmosphere of the Earth by dumping copious quantities of carbon dioxide, but the effects of this will linger in the atmosphere, not just for years, not just for centuries, but 100,000 years. Now, what does it mean? What does it mean for us to live in a world with that much carbon dioxide and that much global warming? So once again, the special guest is Dr. David Archer of the University of Chicago. The book is called The Long Thaw. Professor Archer, as a youth, how did you first get interested in science, and in particular, earth science?
I guess I looked to the Earth, the functioning of the Earth, the stable geochemical cycles of things like that, as something that's bigger than people are. I look to the natural world with a sort of reverence, and I think that's what brought me into the natural sciences. Why I chose to study the oceans, actually, instead of forests or other planets or stars or something like that, is because I've always had a romantic love of boats. But now I ended up living in Chicago anyway. But that's just one of life's jokes, I guess.
Okay, well, let's get right into it. First of all, what is the relationship between carbon dioxide and global warming?
Well, carbon dioxide traps infrared light that tries to leave the atmosphere. It's like if you put a coat on in the wintertime, it traps some of the heat leaving your body, and so it allows your body to warm up. And the theory about CO2, how it affects the climate of the Earth and how much it affects the climate of the Earth, is over 100 years old now. It's very, very solid science. If there were no greenhouse effect, we wouldn't be able to explain why the Earth isn't in a deep freeze, or the climate of Venus, or lots of other things. It's very solid science.
And, well, talking about Venus, some people call Venus the greenhouse planet. Why would a carbon dioxide atmosphere for Venus make it the greenhouse planet?
Well, there's 70 atmospheres of CO2 in the atmosphere of Venus, so it's very, very thick greenhouse forcing. It has a very strong greenhouse effect. Actually, Venus is also a very reflective planet. That's why it's so bright in the night sky. So if there were no greenhouse effect on either Earth or Mars, even though Venus is closer to the sun, it would be colder than the Earth because it reflects away so much of the sunlight that would heat it up.
Okay, well, now let me play devil's advocate. Some people say, bah, humbug. The current warming of the Earth is a natural cycle. The Earth is naturally warming up. Other people say that it's the sun. Yeah, the sun. The sun is causing the Earth to rise in temperature, not human activity. And other people say that the Earth is cooling. What are your thoughts?
Sometimes it's even the same people who one year say the Earth is not warming up and the next year say that it's warming up, but it's entirely natural. You know, ours is a contentious species. We tend to take both sides of positions, even if there's nothing to base assertions on. If they sound good, they still can carry some weight. The Earth has clearly been getting warmer. That's measured, even though it's been a cool summer here in Chicago. Overall, the average temperature of the Earth is rising. The sun has not been getting brighter. We have good measurements of the intensity of the sun from satellites going back a few decades. I don't know exactly. But it's not, there's a sunspot cycle that makes the sun brighter and cooler over 11 years, but there isn't a long-term trend at all in the sun getting brighter. So, you know, people say what they, you know, think people want to hear, and people hear what they want to hear, but there is, you know, objective reality. We can measure these things and say what's really going on.
Okay, well, some of the critics say, okay, so maybe the Earth is getting warmer. However, human activity, some people would say, no, it's not human activity. So what's the reason that many scientists believe that it's human activity causing the current warming?
We can estimate how much warming to expect from rising CO2 concentrations in the air. That's actually boiled down into a number called the climate sensitivity, which is how much the climate would warm if you doubled the CO2 concentration. And the first estimate of the climate sensitivity of the Earth actually goes back to Svante Arrhenius in the year 1896, over 100 years ago, who predicted that doubling CO2 should raise the temperature of the Earth by about 6 degrees centigrade. And now they say it's something like 2.5 to 5 degrees centigrade. It's really not that much of a change. It's a tricky calculation because it's very complex the way that CO2 interacts with light. But this is, by sort of normal non-political rules of science, this is a done question.
So if you, let's say, were to remove humanity from the planet Earth, then you're saying that the Earth would not be so warm as it is today?
There was a model exercise conducted by the Intergovernmental Panel on Climate Change. So these are climate models developed all over the world, and they all subjected their models to one scenario where you tell the models about the rising concentrations of greenhouse gases, and then another scenario where you only have the natural climate forcings like the intensity of the sun or volcanic eruptions can cool down the planet. And if you tell the models about the greenhouse gases, they can explain the warming that has been detected since sort of the 1970s. The temperature since the 1970s, that's the smoking gun for global warming. If you don't tell the models about the the greenhouse gases, they don't warm up in the same way. So if you want to say that the warming is real, but it's caused by something that we don't understand in the climate system, which there will always be things that we don't understand. Not only would you like to come up with an explanation of what that something would be in order to settle the question, but you would also have to figure out why the CO2 is not causing the warming that we attribute it to. It's sort of like if you catch, I make an analogy in my classes to a murder mystery, because people always put on their thinking caps when they're reading murder mysteries. They don't always put on thinking caps when they're thinking about science. But so you catch the butler with the gun in his hand and the dead guy, and there's smoke coming out of the gun, and your partner is sort of a contrarian guy. You're a policeman trying to solve the crime. Your partner says, well, I think the chauffeur did it. But for your partner to convict the chauffeur, he's first going to have to explain to the jury what the butler was doing with the smoking gun in his hand. In other words, translating back out of the analogy, if we want to say that the warming is not from CO2, we have to explain what's wrong with greenhouse theory, that the CO2 should not be causing the warming.
Well, if you look at temperature rises over the last many centuries, you see a gradual warming, because after all, there was an ice age 10,000 years ago. But some scientists say that there's a spike that is quite anomalous that is taking place in the last 100 years, and that's proof that it's human activity, because it's not part of the natural cycle. What are your thoughts?
Well, there is this large-scale glacial interglacial cycle that you refer to. There's also a sort of a milder, much shorter, I don't know if it's a cycle or just sort of fluctuations, but back sort of between the 1300s and the 1700s was a time of generally cool temperatures called the Little Ice Age. So you could, ice skate in Amsterdam and things like that you no longer can do. And that is correlated with a lack of sunspots, which indicates that the sun was cooler. We don't have satellite solar intensity data going back to the 1600s, but we have observations of a number of sunspots that date back to, Galileo's invention of the telescope in the 1600s, and there's a correlation between the number of sunspots and those sorts of climate changes. I think the evolution of climate up until the 70s, though, can be explained pretty well by natural forcing. It isn't until the 70s that the climate signal the human-forced climate signal started to come up out of the noise of natural variability.
Now, also, some people say that the last decade was perhaps the hottest decade ever recorded. How far back does that go? Because, of course, perhaps during the dinosaur era, things were a lot warmer back then.
Sure. So there are thermometer records that go back to about 1860 from Fahrenheit's invention of the thermometer. They can piece together the temperature of the Earth going back further than that with what they call proxy records of temperature from the widths of tree rings or from chemical measurements they can make in ice cores or sediment cores or something like that. And so they can record, they can figure out that the Little Ice Age was cooler, and then there was a period of general warmth before that called the medieval optimum climate. Those records generally go back 1,000 or 2,000 years, and the conclusion of the last IPCC report, which summarized climate, for non-specialists and for the community outside of your own field, very useful, very, very authoritative reports. They concluded that current temperatures are warmer than they have been in 1,300 years. But if you go back millions of years, you're absolutely right. During peaking about 50 million years ago, the Earth it felt tropical to the poles, and there was no ice anywhere to be found. And this is thought to be due to higher CO2 levels in the atmosphere at that time. We don't have as good ways of estimating what the CO2 concentration was when you go that far back in time, but the evidence that has been pieced together is all consistent, that there's sort of million-year or tens of million-year fluctuations in the natural CO2 levels of the Earth that sort of drifts up and down like that.
Now, scientists that have gone to the poles to extract ice cores, essentially getting ice that was deposited perhaps several 100,000 years ago to maybe 1 million years ago,
yes,
they see that carbon dioxide levels and temperature levels go up and down in unison like two roller coasters. What does that mean?
It's rare that you find such beautiful correlations in nature, I think. It's just astonishing. Al Gore showed this plot in his movie. That's sort of how iconic it is. It's an astonishing thing.
So, Professor Archer, ice core data shows that carbon dioxide levels go up and down. But the temperature of the Earth goes up and down, and the two of them go up and down like two synchronized roller coasters. So what does that mean if the ups and downs of carbon dioxide exactly mirror the ups and downs of temperatures on the Earth?
Somehow, the orbit of the Earth around the Sun has these wobbles in it, and that is thought to pace the progress of the ice age cycle, when the ice sheets are going to grow or when they're going to collapse. But somehow the CO2 concentration of the air follows along with the changes in the climate, so that when the orbit tells the ice sheet to make the Earth warmer, the CO2 says, okay, I can pitch in some to that too, and so it amplifies these climate changes.
So which comes first? The temperature rise comes first, and then the carbon dioxide rise, vice versa? What's the relationship?
It's a back and forth cause and effect. It's a feedback system. So to ask which one is driving which, I think, is like asking if you see two figure skaters, twirling each other around on the ice, to try to analyze the trajectory of one without paying attention to the other would make no sense. On the deglaciation, the transition from the ice age climate to the present day climate, the first thing that started to happen, as recorded in the Antarctic ice cores, is a change in temperature in Antarctica. And then a few centuries later, the CO2 concentration started to rise. But then the total change in climate took much longer than a few centuries. So there's no way you could explain the climate transition from the glacial world to the interglacial world without taking into account the change in the CO2 concentration. So it's a feedback loop of cause and effect. It isn't just one or the other drives the thing.
So, summarizing, if you were to go back 10,000 years, we had the Ice Age. Things have been warming up in the last 10,000 years. But it is safe to say that recently, in the last several decades, there's been a spike in temperature rise, and that's due to human activity.
That's more or less true. Actually, the interglacial period is called the Holocene. And the early Holocene, right at about 10,000 to 6,000 or 8,000 years ago, may have been warmer than today. The Earth's orbit around the sun was in a different, slightly different configuration than it is today. So it almost seemed like there was a peak in warming, and then maybe a little bit of gradual decline driven by the Earth's orbit over the millennia. But certainly over the last 1,000 years or two, the temperatures of the last decade are anomalously high.
Okay, let's talk about the present. What's happening with glaciers and the North Pole and the South Pole? We see evidence of the melting of the glaciers around the Earth. That's why scientists are finding so many mammoth bones and even human remains, because the glaciers are receding. So what evidence do we have that the Earth is warming?
Well, we just have the thermometers. I mean, for direct measurements of temperature, thermometers are hard to beat. But the mountain glaciers are almost all melting. It's difficult for a glaciology graduate student to find an advancing mountain glacier to study anymore, because there are very few that exist. There's warming detected in the deep ocean. Fairly deep, not all the way to the bottom of the ocean, but you can see the warmth sort of penetrating the ocean. In the high latitudes, the Arctic is melting like crazy. It's the sea ice covering the Arctic Ocean is melting much faster than any of the models a few years ago predicted. The year 2007 was a sort of a train wreck for the sea ice up there. It just plummeted. Actually, in the southern hemisphere, it's not so clear what's going on. In the interior of Antarctica, it actually is cooling, which is not. That's something that the climate models also predict. So that's not a discrepancy. But there's also not been a melt back in the sea ice in the Antarctic either. And I gather there's still some messiness about that issue, that maybe it's caused by changes in the circulation of the atmosphere caused by the ozone hole, which is a completely different sort of phenomenon. Ozone is it's a greenhouse gas, but it also absorbs ultraviolet light, and so it heats up the air that it's in the stratosphere. That's why the stratosphere gets warmer as you go higher up in the stratosphere, because of ozone. So by wiping out the ozone in the spring of the Antarctic every year, that changes the dynamics of the air, and maybe that's responsible for a lack of global warming signature generally in the southern hemisphere. Actually, there has been very intense warming on the Antarctic Peninsula, which kind of sticks out from Antarctica up into the slightly lower latitudes. And so you read sometimes in the newspapers about these ice shelves. They're very thick, floating shelves of ice, hundreds of meters thick. You could walk on it and not know that you weren't on solid land, that suddenly have been collapsing. Places that have been covered by ice for since the last ice age, suddenly are ice free. So there are signs of the climate change every place. The growing seasons have gotten longer. The Arbor Day Foundation has published maps of climate zones of where you should plant begonias or tulips or whatever, and those have changed since 1990. There are all kinds of signs. It's more obvious in some parts of the world than others. Actually, in Chicago, there hasn't been much climate change since the 70s, but if you go up to Alaska, the climate changes have been huge. So, local experience is not necessarily a good guide, but you put it together into a global average, and it's very clear.
And also, you mentioned how it affects plants and also animals with the changing of the growing season, but also insects, right? Some people are saying that the West Nile virus, which has been spreading through urban centers, is in part driven by global warming, and then in the future, malaria could also spread. What are your thoughts? I'm
not a public health person. I don't really know a lot about the details of this, but people that I talk to are very concerned about the effects of climate on public health. I think the World Health Organization estimated last year that there are 150,000 deaths a year that can be attributed to climate change. Now, obviously, that's a statistical sort of question that's not so easy to answer. But the people that I talk to say that's a very realistic. They have models of disease transmission and everything, and the climate and the insect vectors that carry the diseases are part of those models. Now, that being said, you can do a lot about malaria itself just with mosquito nets and insecticides and things like that. And so I have heard the argument that instead of paying to reduce CO2 emissions, we should just pay for mosquito nets. I don't think the tropical diseases are the main reason why we want to worry about changing the climate.
Okay, now let's talk about the thrust of your book, which talks about the future, up to 100,000 years into the future. Well, first of all, let's talk about the coming decades. What's happening with the temperature on the Earth? Projections out to 50 years, 100 years. Some people say that on a scale of decades, major metropolitan cities like New Orleans, Boston, New York, San Francisco could be partially underwater. So what are the projections for, let's say, 50 to 100 years?
Well, one of the big uncertainties there is what we do with CO2 emissions and energy, but you can take as a baseline just to talk about what they call a business as usual scenario, which is a projection of how much energy people will need and how much fuel they will burn to get it. if there were no constraint from changing climate. And the temperature changes responding to that would put the Earth warmer than it has been in millions of years. So saying what exactly the impact of that would be on, the corn harvest in Iowa or something like that is really not a very easy thing to do. With respect to sea level, the question is all how quickly can the major ice sheets respond to the changes in climate. The models that have been developed in the past don't respond nearly as strongly as the observations that glaciologists actually can make in Greenland and Antarctica about how the ice streams flowing into the ocean respond to the changes in climate. You can measure more ice quakes in Greenland with seismometers than you could 5 years ago. And the ice sheets, the ice streams flowing from the ice sheets into the ocean are accelerating. So it's really kind of anybody's guess how long it takes for sea level to change. There were events in the past called Heinrich events when the Laurentide ice sheet, which was in North America, every 8,000 years or so during the last ice age would just collapse into the ocean. And there would be this armada of icebergs in the North Atlantic, and they would carry little rocks and sand and stuff like that would then deposit on the seafloor, and there's no way for those to get there other than these icebergs. And so that's how we know about these events today, is by finding those layers of rocks on the bottom of the Atlantic. Those seemed like they took a century or a few centuries, and they seem, some of them, to have raised sea level by many meters, which is much more than any of the ice sheet models predict for the global warming climate event. But I think a lot of people, most everybody, thinks that these ice sheet models are just lacking some essential physics at this point.
Well, some people say that the real problem with sea level rise is simply the thermal expansion of ocean water with the rising temperature of the Earth. And since the Earth is rising in temperature, the oceans are going to expand no matter what happens to the North Pole or the South Pole.
Well, that's absolutely true, and that's part of the forecast for sea level rise by the year 2100, which is about half a meter or so. Something like half of that sea level rise is caused by exactly this effect, the expansion of the seawater. It's like the mercury in a thermometer that fills up more of the thermometer when the temperature goes up. That's a process that will keep going for centuries. So the forecast for the year 2100 is not sort of the end of the line. That's sort of just the beginning for the thermal expansion of seawater. The other half of the sea level rise that's actually in the IPCC forecast for the year 2100 is melting of smaller mountain glaciers like in the Andes and the Alps. And actually a lot of the sea level rise today can be attributed to mountain glaciers in the state of Alaska. It just happens to be a place where there's lots of ice frozen on mountains and where the climate changes are very intense. But it's some astonishingly large fraction of sea level rise comes from Alaska.
Well, I'm afraid that's it for Exploration. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics, and you've been listening to Exploration with Dr. David Archer, author of a disturbing book called The Long Thaw.